Okay, folks, we're gonna take a look at Chapter 5's homework. Includes problems 1, 3, 4, 5, 8, 10, and 14. So, we'll go ahead and get started. Some of them are a little bit more self-explanatory than others. Document. Huh? Oh, okay. Problem 1. Problem 1 reads as follows. The tropospheric processes discussed in this chapter cannot be considered as independent reactions. Discuss the relationship between the production of nitrogen oxide species and the formation of acid rain, and the role played by carbon monoxide, methane, and the hydroxyl radical. So, basically here, we're looking at, like, the role of CO, CH4, and OH radical and how it interacts with NO, NO2, and nitric acid. So, such that, for example, NOx, various nitrous oxides can help produce OH. They produce OH radicals, but and these OH radicals can then react with NO2 to form nitric acid, though. So, while the various NO and NO2 can form OH radicals from water and other things, the OH radicals can then remove this in the form of nitric acid. That methane can react with our NOx to form aldehydes, to form our RCHOs, which is going to be responsible for smog, but also methane interaction with NOx can also convert NO back to N2, as can CO. CO plus our various, like, two NOs can go to, like, for example, NO2 can go to NO and CO2. We can convert that back in various ways. That methane and formic acid can react with methane and formic acid, which is a type of over-oxidized aldehyde, can react with NO3 to form nitric acid as well. To form nitric. Generally speaking, but the more of these guys, of the CO and the hydroxyl radical that produced by smog, the more ozone and aldehydes that will eventually help convert these to acid rain. So, kind of a feedback effect on this. So this is kind of more of a thought process on this, without going into too in depth of looking at the individual reactions. Now, with that in mind, now for problems 3 and somewhat of problem 4 and 5, these are more math-centric problems. So 3 has us looking at the mean pH values of these two cities in China are is 3.9, 4.0, 3.8, 4.1, 4.0, 4.5, 4.5, 4.1, 3.7, 3.8, 3.7, and 3.4. 2, 3, 4, 5, 6, 11, over a 12-month period. Over the same year in a different place had numbers of 4.3, 4.4, 4.4, 4.2, 4.5, 4.9, 4.9, 4.6, 4.8, 4.3, 5.4, 5.4. It says calculate the mean monthly pH of the two locations. What is the ratio of these? The mean hydrogen ion ratio of the mean hydrogen ion activity of these two sites. And then what is more likely the most important anion of the rainfall in the urban site. The trick here is not just a simple average, but because this is pH is a logarithmic scale, we have to convert these guys into concentrations. So to convert a logarithmic, you're going to say 10 to the negative pH is going to be the H plus, and then we're going to calculate the H. So 10 to the negative 3.9 plus 10 to the negative 4.0 plus 10 to the negative 3.8 plus 10 to the negative 4.1 plus 10 to the negative 4.0 plus 10 to the negative 4.5 plus 10 to the negative 4.5 plus 10 to the negative 4.1 plus 10 to the negative 3.7 plus 10 to the negative. Okay, well, we're going to have to figure this out and then do the next one. Plus 10 to the negative 3.8 plus 10 to the negative 3.7 plus 10 to the negative 3.4. 3.4. Now, divide that by 12. And you get a average H plus for the first one of 1.385 times 10 to the negative fourth. I take the negative log of that to get that back into pH. That's a pH of something like 3.858. And so, now, we'll do the same thing real quick with the other guys. Same thing with the other guys. I'm actually going to work it out on a spreadsheet, which will make this a lot faster. But 0.9. But if you did the average without the logarithm, you got something that's a little bit higher. I got like 3.96. So I'm going to double check my number as it is. So equals 10. Make sure my calculator didn't crap out being too average. Okay. Now, and then the negative log of that. Okay. Yeah. 3.858. So, doing that again. I just wanted to check my numbers. Doing that again. You can literally, if you put this into a spreadsheet, you can put all the numbers in, have it convert them all into, very easily, convert them all into let's see if I can show you this. How easy it's going to be to show you this. Let's see. Okay, let's see. Okay, let's see. The problem is. Okay, there we go. So you see right there on that bottom half, this is all my pH measurements for the second reading. So I can type in here equals 10 caret, which raised to the negative this value, and that's my pH value, and that's going to calculate, oh, that's my pH. Now, since it's referring to a box and not a number, when I drag this down with the plus sign, it does all my calculations for me. I can then type in what is the average, equals average, and highlight all of these values. So what is my average? My average H plus value at the rural location is 2.905. I would say 906 times 10 to the negative fifth. And if we turn that back into a pH by saying negative log base 10, we're going to have, oh, the average pH here is, instead, if you did it the other way, you get, if you just average the value straight up, you'd get 4.7. And I'm getting 4.5, we'll say 4. Where's 4.68? And that's due to the fact of this is a logarithmic scale. It makes it a little weirder. But so, okay, so we got our average values. If we want to look at the ratios of the hydronium concentration, since I already have that up, this equals this. And I would divide this by this, or I can do it the other way around. Equals the bigger number divided by the smaller number. So the urban environment is something like 4.7 times or 4.77 times greater concentration. 4.77 times greater concentration. So, with that in mind, that's a much more significant. I mean, that's a little bit closer to the accurate value. Now, as far as what are the most likely anions responsible for this for the urban environment, we're not really looking at any particular one in particular, other than the obvious options are, when we're looking at why this is 4.7 times more acidic, it's probably due to acid rain. So that could be from sulfates or nitrates. The book doesn't really make a specification of which one, but just these guys are probably higher in the urban environment than, say, the rural environment. So that's what we're looking for number 3. Number 4 is a little complicated, but it's not too bad as long as you understand what we're trying to achieve here. Number 4 reads, the ionic composition in units of milligrams per meter cubed of an atmospheric aerosol in a tropical forest is as follows. Sulfate, 207. Nitrate, 18. Ammonium, 385. Potassium, 180. Sodium, 247. And the pH of that aerosol is 5.22. Use the data to calculate the total positive and negative charge and concentrations of moles per meter cubed, and suggest the reasons that might account for the discrepancy of anionic and cationic charge. So, we need to use the molar mass to convert sulfates 207, nitrates 18, and ammonia on the plus side 385, potassium 180, sodium 247, and our pH, which is going to be hydronium, 5.2. And we need to find this in moles per meter cubed from milligrams per meter cubed. Okay, with that in mind, step 1, use molar mass. So that's actually the most straightforward thing. So sulfate has a molar mass. We have 32 plus 16 times 4, so a molar mass of 96 grams per mole. So 207 divided by 96 means we have something like 2.1, well, we'll say 16 times 10 to the negative third moles per meter cubed. Now nitrate, with its 14 and 16 times 3, has a molar mass of 62. So 18 divided by 62 means this has something like 2.90 times 10 to the negative fourth moles per meter cubed. Now, sulfate has 2 minus, so we'd have to double that. So 2.16, we double that, and we add 0.29. And so the total positive is, the total negative, 4.61 times 10 to the negative third. Now, ammonia. 14 plus 4 is 18. 385 divided by 18. This is 2.1, we'll say 14 times 10 to the negative second. Potassium is 39. 180 divided by 39 is going to be 4.6, we'll say 2 times 10 to the negative third. Sodium at 23, 247 divided by 23. It's going to be something like 107 times 10 to the negative second. And pH at 5.22. This is the hardest one because we have to convert not just the pH into H plus by taking the negative log of 5.22, which gives us something like 6026 times 10 to the 10 to the negative 6, but then that's moles per liter. We have to convert that into molarity. That molarity, we have to convert that into meter cubed. So, with that in mind, there's 1,000 liters in a meter cubed. So if we times 1,000 to this for a meter cubed, this will convert this into the right units. And so even then, though it's still 603 times 10 to the negative third moles per meter cubed. Okay, so we add all these up. 0.603 plus 0.0107 plus 0.00462 plus 0.0214. And you get something like 4.2, off the paper, 4.27 times 10 to the negative second. So we get far more cations than anions. We're off by a factor of like We're off by a factor of like 38 micromoles per meter cubed. It's a huge difference. But one thing we are missing is like the last part is talk about what could be absent. A couple obvious anions that are pretty common are chlorides. We don't see those chlorides represented. And we don't see carbonates. That's another really big one that can be a huge contributor, especially as CO2 being absorbed. So those could be where we're missing the anions. Otherwise, like, we're really high in the cations, but not so much in the anions. Now that's problem 4. Problem 5 is somewhat similar. Problem 5 has us say average composition and rainfall composition in Egypt. Several sites. One of these sites has average rainfall as a pH of 7.24, sulfate of 12.23, nitrate of 5.99, ammonium is 1.85, chloride as 2.9, calcium as 5.3. These concentrations are in milligrams per liter. Doing a charge balance calculation, explain how you would interpret the results. So once again, we're going to convert these milligrams to liter to moles, millimoles to liter, just so we can easily compare these all. Same thing. We have to double the charge of calcium and double the charge of sulfate. So looking at these real quick. Okay, let's do the pH first. So 10 to the negative 7.24, and we times by 1,000 to get this into millimoles. Even then, millimoles is 5.75 times 10 to the third, fourth, 10 to the negative fifth millimoles per liter. So not a big contribution from the H+. But let's look at the CLs. So sulfate, 12.23 if this is milligrams. We divide this by 96. We get sulfate is 1.27 times 10 to the negative first millimoles per liter. Millimolar, essentially. Would have to double that. Chlorine at 2.9 with a molar mass of 35.5. It's something like, well, that one's 8.17 times 10 to the negative second. And nitrate at, we said that one nitrate was 62. Divided by 62 would be 9.66 times 10 to the negative second. So times 2, so times 2 plus 0.0817 plus 0.0966. So we have something like a total anionic charge of 4.32 times 10 to the negative first millimolar. Now in terms of ammonia, we said that was like, ammonia was on like 18, so 1.85 divided by 18. So 1.03 times 10 to the negative first. Nitrate, oh wait, we're not nitrate, calcium. Calcium is 40, so 5.3 divided by 40. It's going to be something like 1.33 times 10 to the negative first. We have to double that. 33 times 2 plus So So this, and in this case, the acid doesn't really count for much. In this case, there is far more, there's far more negative than there is positive in this problem. So the logic here is that we're missing some key items, possibly potassium, definitely some sodium, possibly some magnesium. It all depends on how close to the sea we are. But sodium definitely is probably a big contributor that we are missing. So that would maybe help understand the difference in charge balance. If we actually made sure to measure all of these guys, they should all add up. But that only works if you actually measure them all. And with that in mind, 8. 8 is it's a kinetics reaction. So nitrogen oxide is formed by dissociation of nitrogen dinitrogen pentoxide. For the first order reaction, N2O5 goes to NO2 and NO3. The rate constant is 3.14 times 10 to the negative second. 10 to the negative second. To go to NO2 and NO3 at 25. At 25. And it's 6.88 times 10 to the negative first at 55. Calculate the half-life of the molecule at these two temperatures. Then for a concentration of N2O5 of 3.6 parts per billion per volume, calculate the length of time it would take for the concentration to be reduced to 1 ppBV at a constant temperature. Then calculate the Arrhenius parameters, A and EA. So half-life of these guys, regardless of whatever they do, is T1 half equals ln 2 over K. That doesn't change regardless. So we can find the K. So given the K, we can find those half-lives. So ln 2, if I divide this by my 3.410 negative second, so the first half-life is going to be something like 20.38 seconds. The second half-life, the half-life for the faster one would be something like 1 second. So a lot faster. Now, to calculate a time, the time it would take for a concentration to reduce, that equation is simply ln A sub t over A sub 0 equals negative kt. Now, it doesn't matter what units A sub 0 and A sub t are as long as they're in the same units. So it doesn't matter that we're dealing with parts per billion by volume, because we're just saying ln 1 over 3 of the same units is equal to at negative 3.14 times 10 to the negative second times t. So we're solving for t. So ln of 1/3, 1 divided by 3, and then I'm dividing by my negative k, and so that would take 34.99 seconds. 34.99 seconds, or thereabouts of 40. Oh, if I'm starting from 3.6, shoot. Changes it ever so slightly, 3.6 to 1. divided by negative 0.314. So that's 40.79 seconds. I made some other typos. But okay, 40 seconds. And that should make sense. 3.6 in half is about 1.5. 3.6, if I divide it by 2, 1.8. If I divide it by 2 again, it's 0.9. So it's a little bit under 2 half-lives. This answer is a little bit under 2 half-lives. 2 half-lives would put it at 40.779. And so I think there's maybe a little rounding error on my part, which is why it looks like it's a little bit more. So either way. So about 40.8 seconds. Let me see. ln 2 divided by 0.031. Oh, that's why. That's 22.07. Typo somehow. But so 22 seconds. That 2 half-lives would be 44 seconds or thereabouts. So there we go. Now the last part is a little bit most painful. Find the EA and the ln of A given our equation. Ln K2 over K1 equals negative EA R 1 over T2 minus 1 over T1. And ln K equals negative EA over R 1 over T plus ln of A. We could technically graph this and get the same thing, but we'll just plug these in. Now, we need our temperatures in Kelvin. 25 plus 273 is 298. And 55 plus 273 is 328. So plugging this in, ln of 6.88 divided by 0.314, the relative values, equals negative EA over 8.314, 1 over 328 minus 1 over 298. You got to evaluate this. So ln of 6.88 divided by 0.314 is something like 308 times R, 8.314, times negative 1. And then we divide by our difference in there. Divide by 1 over 328 minus 1 over 298. And we get an activation energy of, so EA is something like 83,620 joules per mole. So, I'm sorry, I'm off the page again. And so plugging these in for here, ln of 0.688 mine equals negative 83,620 over 8.314, 1 over 328 plus ln of A. So we're solving for A. So ln of 0.688 gives you negative 0.374 essentially, times R divided by 83620, and then times by 328. Oh shoot, no, I did that wrong. So ln of 0.688, and I have to add that to the whole thing to the other side. I can't multiply because then that would be screwing up that part. So with that in mind, I'm going to add my 83620 over 8.314 divided by my 328. When I add those all to the other side, I get a positive 30 something, and I have to take the inverse log. The inverse log puts my a value at something like 1.43 times 10 to the 13. It's a big number. It's ridiculous, but it's there. It's done. It can be done. It can be done. It's annoying, but it can be done. I could also graph it to similar effect. Now 10. 10, we get back to a little bit something seemingly more reasonable. 10. Using the Sun-Ox process. How much limestone would be required each year in order to effect quantitative removal of sulfur dioxide from a power plant whose daily consumption of coal, which is 1.5% sulfur, is 6,000 tons. So 6,000 tons, which is 1.5% sulfur. So step one is to figure out how much sulfur would be in that coal. So 6,000 times 0.015 would be something like 90 tons of S. With that in mind, the chemical process is SO2 plus calcium carbonate goes to calcium sulfate and CO2. We need to calculate how much calcium carbonate would be needed per mass of sulfur. To do this. So the mass of limestone per mass. So with that in mind, calcium carbonate, 40 plus 12 plus 16 times 3 plus 12 is 60. So this is a total mass of 100. You need something like 100 grams of calcium carbonate per 32 grams of sulfur. So 90 divided by 32 means you'd have essentially 2.8 ton moles of sulfur. And so you need something like 281.25 tons of calcium carbonate if we were working under the assumption of complete conversion. However, that's how much limestone would need per day. However, we actually need something like so that's about the amount of limestone we need per day. That's simply it. I mean, though 281 tons if we're doing a simple conversion. If we're doing a straight 1-to-1 conversion. Okay. I mean, that's the 100 to 32. So, okay. So the last one is something more like you have to look up and do some things, but it's... So consult the following website and find the sulfur dioxide and nitrogen oxide emissions for a 3-year period, 1990, 1995, and 2000 for your country. Determine the annual emissions of in mass of sulfur dioxide per capita and the mass of NO2 per capita and compare that to the national data, the same ratios for the world as a whole. Do these results lead to any conclusions or policy initiatives related to your country? Note that the database amounts of emissions are given based on mass of SO2 and NO2, whereas many other sources with the same emissions using mass in terms of S and N. So I looked up some of these values for those 3 years, and in terms of SO2, in terms of SO2 for those following years, so in 1990, 1995, and 2000. Okay, if I wanted to look at these guys, it took a little bit of work. But the value of the world versus US of A for SO2 sound like 128. I'm gonna round this point 0.57 million, and this was something like 28.14 million. This was 112.06 mil. This was 23.76 mil. And in 2097.58 mil versus 21.74 mil. In terms of NOx, and the same thing, world versus the US of A. Specifically, I think I did North America to try to make it a little bit easier. 112.99 mil, 27.82 mil, 116.37 versus 27.22, and 118.71 and 25.46. Now by itself, it looks like, clearly those numbers are dropping over time, and but NOx is going up, at least in the world. But let's compare to population of that. I think I also compared US of A somewhere. But the population of the North America, or something like 276 million, and 295 million, and 313 million. So what it comes down to in terms of SO2, the SO2 per capita, per million people, is something like 0.101. Sorry, 102. Then it drops to 0.081, and then it keeps dropping to 0.069. And the NOx in North America, 0.101, 0.092, 0.081. So at least in North America / USA, it is dropping at a gradual pace. Compare that to the world population, where it's 5.33 billion, 5.76 billion, and 609 billion. The world numbers for like SO2, it's on like 0.025, 0.021, 0.018, and the NO2 is 0.021, 0.020, 0.031. So the overall the SO2 is dropping worldwide, but NOx is increasing worldwide. So, but consistently in the U.S. and North America as a whole, we're seeing a dip in these as we're taking initiatives to try to make cleaner air. Now, is it all going away? No. But this is probably due to the Clean Air Act of 1990. And, of course, in 1995, we had the ozone hole reported, so we really tried to clean things up. And in 2000, there was a ban on leaded gasoline in the EU, so that could have contributed somewhat to some of the cleaning up. But as China starts to become more industrialized, as well as India, that's why you're seeing a bunch more of these two-stroke engines that are producing far more NOx than we would maybe expect. And that's why we're seeing that increase globally while the U.S. is decreasing. So that's just some thoughts on that. But with that in mind, have a good day. That is as far as I can get on this. These are the problems.